Hi guys, we're just going to go through a couple of little bits of stuff from our set theory unit, just because I think it's probably going to help out if I go through quickly first. So the first thing we're going to take a look at is how we describe our sets. And sets are always described, or not always described, they're usually described in set builder notation. So set builder notation looks like this. I'm going to say set of x where x is an integer that is just x where x is an integer. Now, a lot of times when we go to say something like that, that's the same as us saying x where x belongs to the set z. That just lets us know that our x is part of z. So this means x is an integer. Now you'll also see some stuff like extra things that get tacked onto it, something like x where x is part of z, in other words x belongs to an integer, and x is less than 0. So now what you have is you have the definition of negative integers. So that means x in this case will be a negative integer. So just because things get set up like that, our descriptions kind of get a little vague. If we want to be mathy about it, we want to be exact. But we want to be able to take things and put them into groups and have a meaning for what we're saying here, for example. So if if I'm given a set, let's say, I can also be described a set like this. Now, so I now have the set AEIOU, so I can write this as A equals x, where x is a vowel. And if somewhere I've defined set V for vowel, then I could just say x belongs to that particular set. So this is just kind of what builds us up for getting all of this stuff done. So it's important that you just take your time and work through that type of a problem. A couple of interesting things to remember just before I clue up for this particular clip is that the two sets are equal if they have the same elements. So if A has 1, 5, 7, 3, 5, 9, and B has 1, 3, 5, 7, 9. Oops. These two sets are actually equivalent because each element of your set only exists once. So the fact that you have two 5s here, so we've got a 5 here and a 5 here, we don't need them both. One of them goes away. The other thing that's not important in the set is order is meaningless in the set. So because of that, these two sets are equal. So A equals B. So see, we have 1, check. We have 3, check. We have 5, check. We have 7, check. We have 9, check. And there are no other sets there. So we know we're good. Now, we also should take a look at the idea of an equivalent set. So if I have A equals AC and B equals CBD. Now, A is not in both of these, and D is not in both of these, so they can't be equal. But because both sets have the same number of elements, they're equivalent. So these are equivalent anytime that our numbers kind of match up. Sets can be, let's see. Yeah, no, that pretty much sums it up for this one. I don't want to go much longer than this for this clip anyway. So I got a couple of more of these about to come, some with some extra, some Venn diagrams and stuff. So talk to you again shortly.